Cloud. All right, so we're recording. And the first thing I wanted to do is that I put this as a PDF file in case anybody haven't had a chance to do coding before. So this is in Mathematica. Mathematica is a free download that you get as a student. So the code is not complete. I'm just giving you the first parts of it. Like if it was a skeleton and you have to build the whole body, I'm giving you the 2 legs to start with, and you have to build the rest. But the idea is as follows. The first thing that you have to do is have a rectangular grid, and it's going to have a horizontal direction of 200. And the other one should be like 599. So if I make it 599, you cannot see the plot here. So I'm just going to put it here at 99 just to show you how it works. So the first thing to do then is you could do this in Python too, right? It's not Mathematica or C++ or Excel, whatever you use, I don't know, for programming, Visual Basic, right? So the first thing is that I have a function right here that is called constant array. So this function, I can right click on it, or when I'm writing it, I can get the help for it. And if I click on it, I get a help button. So this help button opened up this other window right here that has the instructions of how constant array works. So for instance, if I go constant array, the letter C and N is going to generate a list with N C's. What we want here is our constant array to be 0. And then as you can see here, if you go N1, N2, it's going to give you an N1 times M2 array. So this is what we have right now. And I can go back to my Mathematica. And here is what I put. I want a constant array of zeros that is size 200 by 99. So again, you will have to modify this to 599. And then once I clicked on it, it worked. And this is the array because it's very large. It's just giving me one number here that is not the 0. But the nice thing about Mathematica is that it lets you visualize things right away. So the same thing goes for MATLAB, or if you're using other things similar to them. And if I tell it to plot the grid, I see a blank canvas right here. So you see that it goes actually it doesn't go from 0 to 200. It goes from 1 to 200. And then it goes from 1 to 99 because I just want that portion to be plotted. Again, if you have a question about how something works, you can highlight it, right click, and press the Get Help button. And that tells you like what do you want to do? And explains to you what that function is doing and gives you some examples of how it works. So the first step then is to create the array. The second step is to introduce a particle at site 100 and 0. So that's what I gave you in the instructions. But it turns out that Mathematica doesn't like the 0 index, so it's 1. So in this case, it's not 100 and 0, it's 101. So once I do that, I call this particle, instead of being a 0, it's going to be a 1. And there we go. We just changed one particle from being a 0 to a 1 point in the grid. And if I click here, well, actually, this one was already there because I didn't change it, right? But if I click here, you see that my grid went from being empty to now having this little orange dot right here. Questions so far? All right. So then it gets to be into the nice algorithm part. The next thing is introduce a new particle at height 1. but at a random position. So actually it's not at height 1 because we said that 1 is the number above 0, right? But now 0 is 1, so this should be at height 2. So this is located there. And again, this is random integer is one of the functions that it has. This one, if you look in the help, is gonna give you that, is gonna, oh, sorry, I shouldn't have changed that one. I'm gonna pick a number between 1 and 200 to stick my particle in, the new particle. So what this random integer is doing is that it's telling me, what I'm asking the computer is, pick a number between 1 and 200 and store it in LX. And this is a random number. So last time I ran this, it gave me 48. Hopefully, if I do it again, this is gonna be another number, 181. Cool. So now I have to introduce that 181, not at position 181 and 1, but actually 181 and 2. So once I put it at 181 and 2, is there. Make sense? So that's my position, the local position of the new particle. The next step is to look at the diffusion of this particle. So we're gonna diffuse it. And the way to diffuse it, this is the first thing that is key here. I'm gonna pick a direction that I'm gonna move. And it's gonna be, again, a random integer between 1 and 4. And then I have this loop of ifs. And the first if is like, if this number that I pick between 1 and 4 is 1, the new position is the old position, plus move it in that direction, or in this direction, or in that direction, or in that direction. Make sense? All right. So then I'm gonna pick a random number, and when I go Shift Enter here, that's what Mathematica likes, it gives me the new position. So you see, instead of being at 181 and 2, it's now at 180 and 2. All right, so this is basically the same thing. I just stuck it on the loop over there. So I can keep going with this one. And there's another, the next step is to continue this iteration, right? This position should be changing. The position here should be changing until, repeat this step until I get that this particle is gonna leave the cluster. So my particle is down here at 180 something, and then it likes to keep going. And let's say all of a sudden it leaves in that direction. Then I just say, okay, like, you don't wanna be here, you're free to go, and then start again. That's one condition when it leaves this number. So you would make an if loop that says, if this second number in direction ever gets to be bigger than 599, or 99 in this case, start again and take me out of that loop. The second condition is if it hits the floor. So in this case, if this is 180 and 2 right now, or 181 and 2, if it hits the floor, you stick it in there. So let's do that. Let's say it's going to stick to the floor. So again, it pick itself and move in one direction. Now it's going in the other direction. It keeps going, it keeps going, it keeps going. Now it's going back into the, okay. There we go. So it's at 180 and 1, right? So let me erase this because I don't need that one. So now I have to put here 180 and 1 because it's stuck to that one, right? So this is the new position, the new thing. And if I plot my grid at this point, I should have two particles. There's this one, the old one, and the new one. So those were the conditions that you now had to program into this thing with if loops, that if it touches this 1, which is kind of like our substrate, then it attaches there. And the other thing that could happen is that this orange guy could have been floating around and then it attaches to this guy right here. So you have to do another if loop that says after every movement, checks, is there anybody around me? Is there another position in this direction, this direction, this direction around me that I would attach to? And if no, then just keep going. So in this case, if you have, let's say that you have this particle filled in, right? And then you have a new one coming in. So let's assume that this is my grid right here, right? If this is the new particle, if it moves in this direction, it's looking around it and it says no. So let's start over here. No, 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 yes. At that diagonal, I have a friend. So now I'm attaching myself here. And then you bring a new particle, and then you keep bringing a new particle. Questions? So that's what this code is going to do. And you guys can build it with whichever program you like. Python is pretty nice, but if you don't know how to use it, it's really annoying. C++ is really annoying. It doesn't like for you to make grammar mistakes. And here grammar is like you, instead of a comma, you put a colon, something like that. It won't even tell you that you're wrong. And then Mathematica, which has these visualization options, but it also has some issues. So use whatever one you can, get your hands on that you know how to use, or if you don't know how to use, start with this one and build up your if iterations. Questions? And the last thing is that this is that little portion right here, right? At this point, you could once you have all of the steps figured out with Mathematica, then you can automatize the whole thing because you don't want to be clicking 2,000 times. Actually, it's 2,000 times, but and then all of the steps that this random direction is going to take you through, right? So you don't want to do 2,000 times, let's say 100 steps on average for each of them to attach. Enters. You want it to go just like that and automatize the whole thing. So that's what computers can let you do. Questions? So it's very simple, but you have to figure out all of the possibilities. That's what coding is about. All right. So if there's no questions, I can turn this off. And erase one of me.
I think the download link for the Mathematica code to be bugged.
It's a PDF file.
Is it on PDF?
Yeah. So I made it a PDF file. So Paul is going to talk to us about electron lithography. Share the screen.
I was getting a failed to preview, so I'll need to check that.
So yeah, let me know if it doesn't work, but it should be a PDF file because I couldn't upload a Mathematica file for you guys.
Here you go.
Thank you.
Programming or
All right, so today I'm going to be talking about a really cool technique that I found in the book and I did a little bit of research into and thought it was super interesting. And that is electron beam lithography. And so last week, I actually missed Tuesday, so I don't know if anyone covered any of the other lithography sort of techniques. Okay, so I'm going to talk a little bit briefly about what is lithography in general. Okay. So lithography entails the process of patterning features with high resolution and fidelity across okay, I messed up the first sentence of the slide. Anyway, it's a process of patterning features onto some sort of 2D surface. And it's actually, it's been around for hundreds and hundreds of years. It's kind of an ancient process, lithography in itself. It started out with just writing on stone, which I have a picture of actually. And it comes from the Greek words for stone and writing. So this is about as simple way as you could think to put some sort of writing or images onto stone. Just you have some sort of piece of paper with the image you want put on the stone and it transfers over. That's the basic gist behind lithography. So when we talk about condensed matter physics, obviously we're going to look at things at a pretty small scale. And so when it comes to this sort of pattern, this sort of lithography at the nanoscale, the most common type is photolithography. Basically, in this is when the desired patterns are created on what's called a photoresist, which is some sort of photoactive polymer. And I think I talk about in a minute, but the patterns on this photoresist are created usually by ultraviolet light in the form of, or in the case of photolithography. So these patterns are then transferred from this polymer, this photoresist, onto the substrate of interest. Okay. So there are other sorts of lithography that use ultraviolet light, such as direct light lithography. But what I'm talking about today is electron beam lithography. And it's an alternative to UV-based photochemistry, and it doesn't use these photoresists. It does still use polymers and resists. But instead of the big difference, obviously, is that instead of using UV, it uses an electron beam to damage the polymer, which again is called a resist. And after this electron beam is incident on the resist, it's then rinsed for some sort of set time in what's called a developer. And so basically, you get that you shoot this electron beam onto the resist, it damages it, you soak it in the chemical, and then you get basically a stencil, some sort of polymer stencil that you then put onto the substrate that you're wanting to put this pattern on. And there you go, you're able to pattern very small and usually very precise patterns on different sorts of substrates. So a common positive tone resist, which I'll talk about in just a minute, is polymethyl methacrylate, PMMA, and a common developer is methyl isobutyl ketone. That's just so you know, some cool names. But so what I just talked about was positive tone versus negative tone resist. So a positive tone resist is essentially something that's damaged when exposed either to UV in the case of photolithography or the electron beam in EBL. What happens is that this resist is damaged, just like what I just talked about, and then it's washed in a developer, and the parts that were damaged fall out, and you have a stencil. And then you have a negative tone resist, which is not so commonly used, but basically it's the opposite effect, where you have an incident electron beam or UV, and the damaged parts are actually fortified from this electron beam. And so when you go to soak it in the developer, the parts that were not affected by electron beam are actually the parts that fall out. And so you have a stencil that way. Okay. So yeah, just different ways of getting different sorts of patterns that you want. In EBL, electron beam lithography, most of the time you're going to have a positive tone resist. Just usually you can get higher fidelity images that way. So here's basically an image of what I was just talking about, if it didn't make sense. So we have a positive E-beam resist, electron beam resist. So you put on top of the substrate, you shoot some electrons on top of it, and the part that was damaged is what eventually gets washed away through the process of development. Okay. And then for a negative E-beam resist, again, polymer resist layer on top of the substrate, incident electron beams, and then it's washed away and you're left with this sort of stencil. Okay. Yeah.
Could this be, is this development process sort of analogous to the sort of development process that occurs with the, say, old school photography?
I think so. I don't know for sure, but when I was doing a bunch of readings, it kind of alluded to that sort of process of developing film. I think it is a really similar process. I think obviously not using an electron beam when you're developing those photos. Well, yeah. So how does an EBL work? What does a system for electron beam lithography actually look like? Basically, we have an electron beam source, which usually these electron beams are a source of thermionic emissions or some sort of field emission. And you basically go through a set of lenses, right? And these lenses are magnetized because you're dealing with charge on these electrons. So you have to have magnetized lenses. Basically, it focuses down this beam smaller and smaller and smaller until you get to the deflector. And what the deflector is it lets whoever's using it, the user gets to set the coordinates it wants this beam to shape out. So that's another huge benefit of EBL, is that you get to do custom patterns. You get to actually go in there and determine what kind of coordinates you want, the exact shape you want it to trace out. And then again, you have one more lens here. And so you have a super focused high energy electron beam, and it's beamed straight onto the substrate. And again, you make a custom pattern however you want or whatever you see fit. So then, yeah, this image on the right is just kind of what it looks like. You can do, they traced out copper, but you can do any sort of custom image with EBL. And so it's actually very reminiscent of the same way a scanning electron microscope works. And a lot of times for research purposes and educational purposes, a lot of old SEMs are actually transferred over to lithography systems because it has kind of maintained to be a really interesting area of research for the past 20, 30 years, something like that. But yeah, basically the same thing we just saw in the diagram for an EBL system. You have, again, an electron gun or electron source up top, and then you kind of beam it down. You have magnetic lenses, again, to control the electrons. And then it's beamed into very high energy beam to, in this case, you get an image from the electron detector, but in EBL, obviously, you're getting the shape that you want. So why is EBL important? Why is it effective? So the benefits of using electron beam lithography compared to photolithography, which is what I've been talking about the whole time, is that you get incredibly high resolution images, high resolution patterns, I should say. So on average, the resolution possible with EBL is around 20 nanometers. There have been some pretty extraordinary cases, somewhat recently, of really, really good systems that are able to get even sub 10 nanometer resolutions. But there's a lot of problems with it as well, which I discussed briefly in just a minute. But the big thing right now is cost. It's pretty expensive to be running basically scanning electron microscopes just to make shapes and patterns and little resists. And it also takes a really long time because it is such a high resolution, high fidelity process. It takes super long time, so it's just not incredibly efficient. In fact, most of the time, at the moment, EBL is used for making photomasks for photolithography. And what that is, it's basically like another sort of template you put on top of a resist to get whatever kind of pattern you want. So basically, we're using EBL to make photolithography even more efficient at the moment. I actually, for my project proposal, it's what I wrote about, is how we could increase efficiency in this and create a lot of new cool nanotechnologies and stuff. So what has it made? Speaking of that, this is from NIST, the National Institute of Standards and Technology. This is some of the things that they've been able to make using electron beam lithography. So here we have a micro ring resonator for frequency combs. I didn't actually look into what all this is that they're doing with this, but you can see you have a scale here about 10 microns. And then over here you have metalins for ultraviolet wavelengths, which are much smaller. And then, yeah, you have microcavity and a nanobeam optomechanical crystal here. This is all made using the process that we've been talking about, EBL. Okay, so again, super high resolution, small patterns that are incredibly useful in nanotechnology and a lot of semiconductor things that we use in like our everyday devices. That's what is super important about this, is that when you're doing this patterning, it's for like making a processor in your phone or making a processor in a computer. It's for getting those super minute details that you need to make the semiconductor materials work the way you want them to. And so that's why it's so precise. This is from LNES, which is the lab for nanostructure, epitaxy, and spintronics on silicon. So silicon is one of the most common substrates to use EBL on. And so they were able to get incredibly small, like about 7.5 nanometer in resolution, basically like little cavities there. And so again, 7.5 nanometers there, 11.6 nanometers here. And so this kind of resolution is, again, really revolutionary because most of the time you've seen resolutions of 20 nanometers or above. But this is showing like kind of the ultimate capabilities that we have at the moment for EBL. And then again, there's a lot of downsides to EBL that kind of outweigh a lot of the positives to a lot of people. Like I said before, it's a very slow process just because it is so precise and you're doing a whole bunch with a computer to set the coordinates to get exactly how you want the pattern made. So it's slow. And because you're dealing with electrons, when they are incident on the resist, you get a lot of secondary backscattering electrons is what they're called. So basically, you get these electrons, they hit the thing, and all these electrons start bouncing around. And what you get is kind of like a blurred image of what you're wanting to make with the pattern. Basically, you have all these electrons bouncing around, and they'll start to kind of distort the image or kind of make it not look as clear as you really want it to when it actually cuts out.
Kind of like a failure or a pull set.
Right. It's like yeah, you just hit it, and then it's kind of like an avalanche effect. So that's what this picture is imaging here. You kind of get that this incident electron comes in here. A lot of times it'll backscatter, bounce back, and then you have all these secondary electrons from this first collision that end up, again, diluting that image that you want to be so perfect. So yeah, that's all I have. Are there any questions about any of that? Yeah, Casper. Yeah, so what I talked about in my proposal a lot was actually using STMs and some scanning tunneling microscopes and some of these EBL uses. And that allows for some pretty fine images because basically you're using the tip of the STM, because I think, Derek, you talked about STMs, right? Yeah, okay. So they use the tip of the STM, and they basically have some sort of bias across it. It's usually a pretty small bias across it. And what it does is it creates that electron current across the tip to the surface you're on. And that's how you're able to actually etch some sort of design into that. And you get, again, really small, really precise designs that you want. And then there's also a lot of people, or not a lot of people, a newer thing is actually using multi-beams, like different beams and combining them into one. There's a bunch of startup companies that have been working on that, but it's kind of an untapped thing still. Basically, it's just what it sounds like, just using different sources and you're kind of beaming them together. And that way you can, basically you make like complex patterns with one and then combine it with another complex pattern, you get even more complexity. So again, it's looks very promising for creating more and more complex nanotechnology, and we can get faster phones and all that kind of stuff. Yeah.
One thing I was kind of curious, since the sort of the beginning of this presentation was, you mentioned a little bit about the minute differences between photolithography and this electron lithography. I'm kind of curious, what sort of spawned the ideas for doing electron beam lithography? Given that the above mentioned benefits of doing.
Yeah, I think that's a good question. I think the main thing that spurred them on into e-beam lithography was that you can get incredibly high focused energy focused into one point. And the energy is usually on the scale of like tens of kilo electron volts. I think that was really appealing for a lot of companies kind of a while ago. But it's actually interesting that they started being appealed to all this high energy, but it's actually ended up kind of backfiring. It's what creates a lot of that backscattering electron stuff. So now we got interested into it, but now we're kind of trying to back off and figure out some ways of making low energy systems. Does that answer your question?
No, that does.
Okay, cool. Yeah. Yeah. Yeah, it's usually on the order of tens of kilo electron volts. You can get much higher, but not, again, it's kind of detrimental to actually go much higher than that. So usually in most commercial applications of EBL, it's 10, 20, 30 kilo electron volts, somewhere around there. Any other questions?
So you showed a picture with lines that are like 7 nanometers, right?
Yep. Yeah.
So when we look at semiconductor processing right now, if you look at the latest Apple or Intel devices, do you know how big they are, the features that we have?
No, I don't actually.
Like 12 down to 7 now. There's 7 in the Intel. Yeah. So this would be a state of the art. I don't know what year this is from, but it's now the technology that we have. Like the smallest feature of that transistor is when it makes these devices, it's about 7 nanometers.
Right.
I think that
since it's run around on certain processor cores.
Right, so they have SU M1s, something ultra. The next generation is going to know this number.
Yeah.
And the smaller you make it, the more transistors you can pack into your system.
Mhm.
And then they become almost molecular. I mean, look at the sizes there. How big is a molecule?
Like in a couple of angstroms.
Right, maybe 10, 15 angstrom.
Mhm.
So now we have things that are in the 5 nanometers, so they're kind of like a big
Yeah.
molecular transistor.
Yeah, I think this was, if I remember correctly, it's like 2012 maybe or something when this article was produced. So this was obviously really revolutionary at the time. I didn't actually know that it had come down to that size at the commercial level yet.
Yeah, yeah. So Intel is doing this for all of their chips.
Mhm.
Now that's 7.5.
Okay.
Doubt AMD is that far.
Sorry.
I highly doubt AMD is that far behind either.
Yeah,
That's
AMD is
easy.
so yeah, the changes that they have between them might be that they have a different photoresist or different this or that. But they basically are playing with the same instrument.
Yeah.
The multi-billion-dollar factories.
Yeah.
All right, well, let's
Right.
take Paul again. You wanna go? Go for it.
Do you have it in a flash drive? Correct. Cool. Go for it. It's just down there. So let's see, where is it popping out? It's not popping out. Let's see. There we go.
Okay.
Go for it. And you know how to set up the share the screen, right?
Yeah. No, this one. I did this one before. No, this is all presentation.
So you have to start before you shift, go back to that guy,
Okay,
to yours, and then start this one.
this one, right?
Right. And now go back to without tab. I think it's window tab,
Okay.
and go back to Zoom to start sharing that. Yeah. Yep.
Here,
And then now share the right one.
screen.
Share the green arrow
Here,
right there,
okay,
and that,
this one.
and then put this one. All right. Go for it.
Can you hear me? Yes, so today I'm going to talk about focused ion beam. This is a technique can be used in semiconductor and engineering and in material science and like also in physics fields and in science fields as in general. So this change this. Okay, so this is a powerful technique and mostly used in removing material and also designing material or like creating shapes on the substrate. So you can like use this technique for creating shapes like rectangular or circular, and also to study and also deposit material. So so this can be used for imaging because most of most of this technique or most of this apparatus can be used with scanning electron microscope for imaging. So you can bombard the surface of the substrate and then take a picture for the substrate at the same time. So, and also it can be used for milling. Milling sometimes using like to describe the removing material. So when you use this focused ion, use this ion beam, so it can transfer the energy to that substrate, and then if that kinetic energy is higher than the bounding energy of the atom in the substrate, so that can eject the atoms from the substrate. So it can also like sparing the atoms from the substrate. So that we call like milling or also removing material. So micro machining, and also it means here like this focused ion beam, it can like design shape or create shapes like between in the nano scale and also in micro scale. So what is focused ion beam and how it can work? So in this in this technique, they use metal ions, which is generated by liquid metal ion source. So this, they use liquid metal, and this liquid metal can be heated with tungsten needle and then melt this liquid metal. And this liquid metal, when it's melted, it's exposed to high voltage, which is up to like 110⁸ volt per centimeter. This is like a huge voltage that can be applied to that liquid metal, and this gets ionized. When it's get ionized, it just focused, and this beam like can go and focus on the substrate and then remove the material. So, and also the this can be used in performing maskless site-specific structures. It means like when Paul talk about the lithography, so you can design any shape like circle or rectangular or like lines on the substrate without using mask. So here, like in this technique, they must have used like they used to use gallium as the ion source. Why they use gallium as ion source? Because it has like a low melting point. A low melting point means like it can melting like even like at 30 Celsius. So this is one advantage of using like gallium as the ion source in this technique. So here is a shape, like one advantage of this focused ion beam. Here is the designing. So you can use this technique to design any shape that you want. This is one of big advantage of this technique, which means like when you have this ion strike on the surface of the substrate, so and this transfer the kinetic energy to the substrate, and then eject the atom, and then that can create like either holes or like holes in the substrate, and this can like between like 100 nanometers. So as a diameter. So in my project, I use the focused ion beam like one time, and then we are interested in removing native oxide. This native oxide can be deposited on the silicon substrate easily when you just use like cleaning process on the substrate, and then when you just expose this wafer to the atmosphere, just native oxide can be deposited in the material, and this can also contaminate the substrate. If we deposit, for example, like gold or like any kind of like thin film, this native oxide can minimize the quality of the substrate. So this is the, yeah, in this picture, I use the focus ion beam, like we can use like up to like 40 kilovolt. And we can create the shape like here, like you can see, we can create like donut shape. So in the inner diameter, so we use almost 4 micrometer. So here we are like we removing the native oxide in the outer circle. So we use we remove the native oxide, and here we can also, here is the native oxide. Here we can also after that deposit material that we want, and then we will have different properties of materials.
So you remove the oxide in this donut shape, right?
Yes.
How big is
They use current.
no, how big is this? So you have like this thing.
How depth you mean?
How depth?
Yeah, we can use like up to 5 micrometer depth in the silicon substrate.
And this is about 4 microns, you were saying? Because I cannot see the.
Yeah, it's almost like about 4 or 5 micrometers as a diameter. So we can see like inner circle has native oxide, and then outer surface has outer diameter has removed native oxide. So here, like we can after that we can deposit the gold and study the like optical properties of these materials, and we can see the difference between those between like when we don't have native oxide and when we have native oxide in the material. So also one disadvantage of this focused ion beam that it can also one advantage of this ion beam also can be used to study or to study the cross section of some materials, because it can be used for like a high kinetic energy, and this high kinetic energy can damage some area in the substrate, and then you can see the cross section for the materials. And also it can be used for radiation damage. I think it can be used for radiation damage. Some researcher can study their film or like their materials under irradiation, so they can use the focused ion beam in the same time, like when they bombarding the substrate, and they can study the damage on the material. Yep. Any question? So this is the end. Question.
So you mentioned you were be doing this, right?
Yeah, I supposed to get the training started from today, but they rescheduled the training. So I just used one time.
Is it in Venture One that they have it, or where?
Yeah, it's in Venture One. Yeah, we have it in Venture One, this kind of technique. Yeah, go ahead.
How long was this thing?
So you can do like same time, like it didn't take that much time. Like you can just like 5 minutes, you can create this shape or like any shape you want.
What is out of curiosity, are there some potential drawbacks to this method of sort of like drawing images onto material?
So could you please repeat that question again, because I didn't understand.
I don't know exactly how to precisely phrase this, but are there possible drawbacks or limitations to applying this technique when using it to sort of stencil or produce images into a desired material?
Yeah, so they can use a scanning electron microscope to image the material. So is that answering your question or not?
Not exactly. So, but if somebody else does have a question, I can.
Well, I guess the question is asking is, what is it that you cannot do with this, right? So for instance, you can have a resolution limit.
Okay.
Like when you're talking about the filter corrector, like you're limited to a couple of 100 nanometers. In this case, do you have a resolution limit of how small you can make the features?
Yes, so you can, yeah, you can like, you can use measurements to scale, like you can use like up to 1 micrometer or like half micrometer, like to designing the material.
Because I think it is based on how big of a spot you have, right?
Yeah, like in my case, like we are interested like to design the between like 5 micrometer, like or two like between like 5 or like 1 micrometer as a measurement, like for this shape.
Right.
Are there also any power consumption concerns that come with doing this kind of experimental technique? 'Cause I know in in the last presentation, they talked a little bit about the process being kind of a sort of a power hungry process. Like, does this take a considerable amount of electrical power to be able to conduct this type of procedure?
I don't think so. No,
But I think also
Oh,
with
did they?
it so short, right? It's only taking so long to actually do it, even if it was like the same amount of energy, it's still much.
That makes sense.
So any question?
let's think of it again. So, I'll show you guys a figure from an actual research paper because it has to do with what we were discussing in our previous class about the quantum Hall effect. So this is the Hall coefficient from our previous class. This is the last thing we covered in class. And I was telling you how it works, that for negative charge carriers, this Hall coefficient would be negative, right? So you're able to put something in the magnetic field, that's the H. You're able to put in some current, and then you're measuring this voltage or the electric field that is being produced. So once you measure the whole voltage, you can get that electric field EY. And now you can put this into your system. Let me now get the original paper out. So let's look for the original paper. Where's the original? So this is 2020. All right, that's not helping. So this is the first, this is an article in the first paper. And again, they're not showing us the where it is.
Even the American Physical Society.
All right, there we go. This is the original paper. Let me share the screen. There we go. So this is the first paper that came out 2004. Novoselov was the postdoc in Andrew Game's group. Andrew Game is the big boss in this group. And I think I told you guys stories about this group, right? Like Novoselov and how in his research group, they have like on the Fridays afternoon, they have free time in the lab and then they go and do crazy experiments. I told you about him, how he discovered, he has a Nature Materials paper where he has like gecko tape and he put as a cover a Spider-Man hanging because he has gecko tape on his fingers, a Spider-Man toy figure. So this is the same group, right? He also got, Andrew Game got the Nobel Prize for levitating a frog. And he has a Nobel Prize for basically discovering graphene. So here we see a graphene flake on the microscope. Then they use lithography. They have a silicon oxide wafer. No, sorry, a silicon wafer that is highly doped right here. The silicon wafer has 200 or so nanometers of silicon oxide. Then they put this graphene flake on top and use photolithography to construct this hole bar right here. This is called a hole bar. And then they deposited, I think again with photolithography, they deposited these gold pads on it. So this is your graphene, cartoon of how the device is. This is what it actually looks like. So this is gold, this is graphene. You see the distance here is 1 micron. So this pads is where you're putting your current through and when you're measuring voltages. This is the single layer graphene here and here. You can see where it falls. You get double or triple layers. I don't know. It's hard to tell. But people got really good at making devices that they were just a single layer of graphene right here. So let's say that you put a voltage difference between here and here. That means that there's an electric field and you would have particles flying through it inside the graphene system, right? Then you can use a voltmeter and look at the voltage difference between here and here. So that would give you you can measure the voltage as a function of the current flowing in this direction. But then you stick it in a magnetic field and you have that the charges will go in, let's say, this direction. Then you can do a voltage measurement between this pad and this pad, or this one and this one. It doesn't matter, right? It's the same thing. That's your whole measurement that you're doing. Current flowing from here to here. Voltage measurement here gives you the voltage characteristics of that I versus B. And then the voltage between these two pads would give you the whole coefficient that we're looking at. Questions so far? No? All right, let me show you the picture then. So this is the first picture they came up with. This is too big. Let me see if I can make it smaller. All right. So they have here. Oh, there's another thing that I haven't told you. So this is a field effect transistor. This thing right here is a field effect transistor. And a field effect transistor, how it works is that you have a channel right here. In this case, this is the channel where the conductance happens, the graphene flake. Then you have some oxide, and then you have a conductive material on the bottom. Usually it's a metal. So a field effect transistor is also called a CMOS transistor, right? Metal, oxide, semiconductor, CMOS. And what happens then is that you put a voltage from here to here. That just generates current going in this direction. But what you have to is to control another knob right here. So a transistor works with 3 knobs. So you will have your source, your drain, and then here, your gate. So you put a voltage from source to drain, but then if you put a voltage here on the gate, what you're doing is that you're introducing more charges or reducing the charges into your system. So that's the basis of a transistor, a field effect transistor. So in this metallic area right here, they're able to change that voltage. And that's actually what they're doing here. They're changing that voltage and they're looking at the conductivity of the sample. So when the voltage is around here, the conductivity is the minimum. When the voltage is around this area, the conductivity is high. When the voltage is in this area, the conductivity is high. And so they were wondering like, oh, what kind of material do we have? Usually this is an on-off system because we either have that we're mostly electrons in the system or mostly holes. So it would be that when the voltage is high, you're pulling all the electrons out or pushing a bunch of electrons in. And when your voltage is low or in the negative, you're doing the opposite. So they're looking at this and then they said like, oh, we know, we can explain this very well. Probably graphene, because they didn't call it graphene right here. They just said atomic layer of graphite, right? But they thought probably the band structure for it is that it can host both electrons. Right here, this is the band for electrons. These 2 guys are the electron bands. And then these 2 bands are hole bands. So when we're changing the gate voltage, what we're doing, when the voltage is -50, we have mostly holes. When the voltage is +75, we have mostly electrons. Does that make sense? That's what they were thinking that they had. They hadn't looked at the literature and seen that since the 1940s, people predicted something different. I don't think they knew about band structure of graphite, which is the Dirac cones and carbon nanotubes and all of that cool stuff, right? So in this case, they had this. So now you see that this measurement is the Hall coefficient. And over here is positive up to some value, the Hall coefficient. Then it flips sign. When it's flipping sign, they think that it's flipping signs because these 2 overlap, right? And it starts filling up electrons, and then there's also holes right here. So once you have electrons and holes together, it starts coming down. And after it came down here, at this point, from here forward in gate voltage, you would have mostly electrons in the system. So that's the idea that they had. That's what they thought they had. And that's the picture that proves that for them. So we know now that this is not true, that actually is 2 cones. But this was pretty clever. They just didn't know the real band structure. And this is kind of interesting because it's a material that can host both electrons and holes depending on what voltage you're putting on it. Questions? No?
Although,
All right, then let's go back to this thing. So the idea then is that the band structure, right? As a function of some momentum, this is the energy. What they thought they had was something that was maybe like this and this, where they overlapped, right? So this is the holes. This is the electrons. So that's not exactly how it works for graphene. It's actually, and Derek showed us this, right? That for nanotubes at least, right? The Dirac cones, they go like this. And now this is just the overall average of this, that this is the important thing. This is on average, it looks like that. So there's the Dirac cones. Down here is holes being the conductors. So let's say that the Fermi level was up to here. All of these levels are filled, and then all of the levels from here to here are empty. So this model explains what those guys view exactly too. The two models explain the same data, but this is the reality of it. If you change the gate voltage, what you're doing is that you're pumping more electrons in, and then you fill it up to, let's say, this portion. And you have that there's a lot of electrons in the system, and the electron charge carriers will give you a negative Hall coefficient. So the other thing too that is pretty interesting in my view, let's say that this was your sample, right? If you look at it, there's regions of it. And this is because they're dopants between the silicon oxide and the graphite. So this might be mostly positive dopants right here. And then we will have some dopants that are mostly negative. So on average, this might be a neutral system. Or in this case, it's not neutral, right? It's shifted towards the negative. A little bit towards the negative, green would be neutral. But the charge impurities that you have in the system locally gave you that is up here or down here. And it's not a perfect the whole way. There's a lot of impurities in the system because silicon oxide can have a lot of molecules in between them. The Scotch tape, for instance, that they used to take the graphene out, right? When they transfer it into the silicon oxide, they might trap some of the finger moisture, fingerprints, ammonia, trap molecules of something, whatever it is. And that's what they were able to measure by doing this Hall coefficient. All right, so we have a couple of minutes. Let's see, what else can I do? So we have that when we look at this, the Hall coefficient that was discovered by Edwin Hall, it showed that the original data that he had is that the electronic charge that Thomson determined later, it was exactly what Hall was saying. So it showed that they were actually do really measure the charge carriers that are on the system, and it agreed with those ideas. One thing is that when he tried it on some metals, the Hall coefficient was positive, in others it was negative, even when Hall was doing this. So that meant that electrons were not the only thing that were carrying charge, that you could have something with the opposite charge carrying charge. So now we know that that's possible. They're called holes. For instance, if you look at something like lithium, right? Lithium batteries, the lithium is the carrier and it's lithium plus. So that's an ion and that's carrying positive current in your batteries. The Drude model doesn't explain this. You need to use quantum mechanics to figure out what all of this is. So that's not completely helpful. But we can look at the Drude model for the Hall coefficient. So let's start with that. So this is, again, the Drude model that we used before. We're going to have a current density. We have two currents, one going in the X direction and one going in the Y direction. So there's an electric field. One of them is e to the x. This is the one that we're putting in, right? We're putting that one a voltage difference between the two paths or the two ends of our film. And then we're also going to have an e to the y. That's the one that is generated in the presence of the magnetic field. And then we also have a magnetic field. The magnetic field is not arbitrary, it's put in the z direction and the z axis. So if we look at all of this, the force acting on an electron the forces acting on the electrons are given by the charge of the electron, the electric field, plus the velocity cross of the electron cross with the magnetic field. And then we have that, we have to divide it by the speed of light. So now, what I wrote down here, this little f, is the average force. Let's call it the average force. So this is when we have a collection of electrons, even though they're classical particles, not all of them are going to be traveling at the same speed, right? Each electron is going to have a different force because each of them is going to be traveling at a different speed. But for this case, let's just assume that we have an average one so that we can do calculations and not worry about doing things that are too complicated. So we're going to have an average force per electron. So if we have that equation, right, we can now write what is the momentum. So this is the Lorentz force. And we can now write the momentum per electron. So we're going to have the change of momentum with respect to time is equal to this electronic charge negative. We have the electric field. We have the momentum here. So notice that it's the same as the velocity divided by the mass, right? We cross that with the magnetic field. And then we also have that our momentum has a drag force, right? Acting on it. So that's the Lorentz force. And our equation for momentum has this term right here that is the drag force from the collisions that is opposite the momentum. So just like before, right? We're just adding the magnetic field in there. So we are looking for solutions of these equations. These are coupled equations because this has electric field in the X and the Y direction. And then our momentum is in the X and Y direction. This magnetic field is in the Z direction. We can look for solutions in the steady state, and I think I covered the meaning, right, of a steady state. Can anybody tell me what it is that is meant by steady state? You guys remember? No? So after things have had a chance to equilibrate, right? So for instance, when we turn on the voltage, when we turn on the magnetic field, we knew that the particles were moving in that direction, right? But then they accumulated enough so that now there's a voltage going in that direction across it. and the particles are not going to be accumulating anymore because the two forces canceled out. So that's exactly the same thing, that the two forces are going to cancel out. That's the steady state solution, the one that happens after things have settled down. And it's not when you turn it on at the beginning, but it's when things have settled down. So that means that there's no change. It's a steady state. That means no change, right? Things are settled. And that means that I can put a 0 on this dp dt. And then I have the x component of my electric field. And then when I do that P cross H, I'm actually going to put MC and all of these components here into this omega C Py minus Px over tau. And a steady state again, so this dP goes to 0. And now you see why we want to solve it in the steady state. This is a cross product. So there's a negative portion, there's a positive portion. This is the one that goes with Px. We have that. And then omega C is all of my constants stuck together. So now you see why we want to do it and the steady state, right? Because then I don't have to, it's a steady, so I don't have to worry about changes in time. And therefore I get a 0 here and 0 there. So once I have all that, I have my solutions in the steady state. And what I'm going to do is multiply both equations by n e tau over m. And you've seen that one before, right? This is the omega naught. And once I did that, I can rewrite it as, oops, omega naught e to the x is equal to omega c tau, current going in the right direction, plus current going in the x direction, and omega naught ey is equal to the negative of this omega c tau, current going in the x direction, plus current going in the y direction. So this is drew the DC conductivity from before. And I used the definitions from a while back of what this current is, and this current is related to this guy and this guy, right? That was how we settled on what sigma naught was, that it was the relationship between this guy and this guy, the proportionality. So now that we have it this way, we see that the whole field is measured when there's no current going across this one, this transverse current. So that means that we can set 1 to 0. So we're going to require that GY goes to 0. And that means that oh, I only need this equation right here. So I'm going to bring EY is equal to, this one went to 0. And I have negative omega c tau divided by omega naught times gx. So now, remembering what omega c was, I can rewrite it again, and I have a negative h, the magnetic field, the concentration of electrons, the charge of the electron, and the speed of light, Jx. So, since the Hall coefficient is, and this is the formula from before, where this Hall coefficient is given as the ratio between the transfer field and this current times H. If I do this with this, right? Then, knowing this formula and this formula, right? Now I have that the Hall coefficient is equal to this value. So let's talk a little bit about this, and then I'll let you guys go. What do we see here? The Hall coefficient depends, this is really cool, actually, because the Hall coefficient depends only on this constant, right? The electric charge, this constant, the speed of light, and the carrier density, how many electrons per unit volume you have on your system. The density of the metal, the carrier density of carriers in the metal. So we know, let's say we have a chunk of gold. We know how many conduction electrons it has, gold, right? And therefore we can calculate what this value is and then compare whether this Hall coefficient that we can measure agrees with the number of electrons per unit volume in gold we should have, and on the other metals. So by doing that,
This would be characteristic for all gold atoms.
right, that's just because you have gold with that metallic conduction electrons, that many of them. So by doing that, you could prove whether this theory is correct or not. There's no mention of tau here. Tau went away, which is the problem that we had when we were talking about what Rude did. Taus cancel out. So now, because you have a tau and a sigma node that are here, right? So the taus cancel out. So now the theory doesn't have the problematic point in it. All right, so that's where I'm gonna leave you guys with that this is some very nice result. And it could help validate the assumptions that were made, because everything else aside from the tau was not problematic. Questions? All right, I'll see you guys.